Hello there. So this video is possible speculation on my part. I say possible. To me, it's speculation. I have this intuitive idea. Okay. Now, I wouldn't normally talk about it because it's too, for me, until very recently, it was too sort of up in the air. It's just an intuitive idea, very speculative, and I would have had a lot of trouble trying to really explain it exactly. But I was reading this book, Vertex Operator Algebras and the Monster. Kind of a famous book, low-key famous. And, well, there were some things said in here that, to me, tell me I'm on the right track with this speculation. It's basically what I was thinking. And so, for that reason, I'm willing to talk about it. Because, yeah, well, you'll see. So we're going to be talking about E8 and maybe some of the special characteristics of E8. And for those who don't know, E8 is sort of the biggest sort of fundamental symmetry. Okay, I'm using non-technical language, obviously. But I can't explain in total depth right now about what exactly all that is. I have past videos here about Lie groups and stuff like that, where you can look if you want to know what a Lie group is. But E8 is a Lie group. It is by far the most complicated of the sporadic Lie groups and or Lie algebras, E8. So we will be talking about that. And there is apparently a sort of special characteristic of E8. Now, what I'll do is I'll quote from this book real quick. Now, I'm going to be drawing in the program behind here afterwards, but I just wanted to bring up this book. So I'm going to quote from it real quick. So, well, we're talking about E8. We're talking about the monster. So the monster is the largest sporadic finite group. Okay. I guess its simplest representation says here, here's a quote. Greece Conway, so I'll say this is page 22 of the introduction. Greece, Conway, and Norton then noticed that the minimal faithful representation of the monster would have dimension at least 196,883. Okay. So that's the minimal dimension of the faithful representation of the monster. And so there's this... so it's quite interesting that we even found this thing, and I'm not clear yet on how exactly it was found. That there must be an interesting story or many interesting stories related to that. And, you know, Conway, who I believe passed away in 2020, was it from COVID? I don't know, but Conway was talking. I saw an interview with him where he was saying before he dies, he hopes he would understand why the monster is there. Basically, yeah, because it seems mysterious. We discovered the largest sporadic finite group, and it seems to come out of nowhere in a naive, sort of on-the-face level. Of course, math doesn't just come out of nowhere, right? It's not just arbitrary randomness. So there's definitely some things going on. And in some way, the monster is connected in some ways with E8 and lattices related to all this stuff. So I'll briefly say that basically what we're talking about is the study of symmetry. And, of course, there's group theory, okay, and the study of finite groups. And then there's mathematicians realize that, an obvious question was, are there sort of continuous groups? And this was developed into, we call them Lie groups. And so then it was discovered, I think Sophus Lie is the one who figured this out, that you could, instead of studying Lie groups directly, you can study their Lie algebras, which are the Lie algebra is sort of defined by the tangent space at the identity. So the idea is that, and I've said before, when I think of Lie groups, I sort of think of rotation spaces, but it doesn't just have to be rotation. A skew transformation would also be something to look at. And so, for example, a very important Lie group is just the general linear group of n dimensions, which is the group of linear transformations that are invertible for a vector space. So you have a vector space, and yeah, I'm not going to explain that more. These are prerequisites to this discussion. But you got to start somewhere and end somewhere, right? But anyway, so the Lie theory side, where you use Lie algebras in order to study Lie groups, that's one side of things. Then there's the Coxeter systems or Coxeter groups, which is it's basically about the study of polyhedra or n-dimensional polytopes, really. And so Coxeter was very interested in sort of, more dimensions than 3, lots of dimensions, and what kind of regular polyhedra, but when it's n-dimensional, you call them polytopes. So what kind of regular polytopes do we have? Like, what are the analogs of the Platonic solids in higher dimensions? That's a really good, interesting question. It's amazing and kind of sad that we weren't, mathematicians weren't figuring this stuff out like 300 years ago, but they weren't. Anyway, Coxeter systems, really interesting. That is a more, let's say, and I want to zoom this in here because I think it does better, maybe for the algorithm. It's a bit of a pain. Try to sort of zoom in a bit here. So, Streamlabs makes it a little difficult. Maybe not the best. Maybe I regret this. I'm going to go back. Sorry I'm not editing this video. If I get over 500 views on these, I'll start editing them. Okay. So, where were we? So, Coxeter systems. I'm just going to write that out. So, we have Lie theory. Okay. And Coxeter systems. And I've talked about this in past videos, but, don't switch what you're watching right now, because it's a doozy. Coxeter systems. There is, yeah. And there's another way of looking at and studying these symmetries, which is lattices. And that's sort of where I am now. I wouldn't say that I've mastered Lie theory and Coxeter systems, but I know a lot about it. But there's definitely a lot more work to do. I need to dig into them again and master them at some point. But then right now I'm kind of diving into lattices, and this is another way of studying these symmetries. And these are kind of the 3 main ways I know, and there's a lot of overlap here. It's not exactly like a one-to-one correspondences here, but almost. And there's a lot of overlap. So these 3 ways of studying symmetry. And we're talking about, well, I'm thinking of it as continuous symmetry, but I don't know. I guess these aren't really. Well, these are sort of analogous to the Lie algebra side of things. Okay, so yeah. Okay. Now, then here's another quote from this book. On the next page, McKay and Thomson conjectured the existence of a natural, infinite-dimensional representation of the monster. So that's very interesting. An infinite-dimensional representation of the monster. Now, in some way, I'm pretty sure the monster is related to E8. So, if I'm wrong about that, then the rest of what I'm going to say today is pretty stupid, probably. But, yeah, like I said, I'm in the process of learning this stuff. And there's going to be some speculation here. But, okay, so we have the dodecahedron. I wish I could draw that. we've got the sort of the cube and the octahedron. I'll just write octo. So these are duals of each other, so they're basically the same symmetry. You have a tetrahedron. Right now we're only talking in 3 dimensions. This is self-dual. Okay, and then you have the icosahedron / dodecahedron. 2 different objects, but they're duals to each other. Dodecahedron. And so these correspond to certain, basically certain Coxeter systems, and roughly they correspond to certain Lie algebras. Okay, but the correspondence is well, with Coxeter systems, it's less of a correspondence and more. This is at least how I think of Coxeter systems. I guess you don't have to. Coxeter groups. Okay, the group symmetries of these objects will be the same as the Coxeter groups. Okay. Whereas the Lie algebra side of things is a little more. You need to think and study a bit to see the correspondence. But so here, and I hope I don't make any mistakes. I'll try not to, but there might be. And check the description in the comments. If anybody notices a mistake, let me know. So here, when I think of a tetrahedron, I'm thinking of a symmetric group. Okay, because basically, and by the way, well, I'm using this in 3 dimensions, but we have an eye on the higher dimensional cases as well. Because a tetrahedron, how do you make a tetrahedron? You have 3 points, and then you just connect all of them. And so, it's my beautiful drawing of a tetrahedron. So if it were in 4 dimensions, you're going to have 5 points, and every vertex is connected with an edge. So it's rather... so like, we'll talk about the cube case, and in higher dimensions, how do you decide on how the vertices are connected? How do you decide where there are edges and where there aren't? Well, so here's a cube. One way to do it, which I think is the way probably everybody does it, you can think of this as having... We can think of somewhere as being the origin. So here's 0, 0, 0. Okay? And all the other vertices are... well, basically, you can have a 1 or a 0 in each slot. There's these 3 slots. Each one gets a 1 or a 0. So 1, 0, 1 is a valid vertex. 1, 1, 1 is the opposite vertex. So over here, right? So we have 2 to the 3 possibilities. We have 8 vertices. Okay? And then so in 4 dimensions, then that pattern resumes. 2 to the 4th equals 16 vertices in 4 dimensions. That's the hypercube or the tesseract. The 4-dimensional hypercube, also called the tesseract. So to figure out how the edges connect, what you do is you compare vertices, and whenever they differ only in one of these slots, then they're connected. If one and only one, then they will be connected. You kind of think about the cube and how that works out, right? Anytime you go from one vertex to another, you're changing one of these slots in these 1s and 0s. So I know this was a little bit quick, this explanation, but hopefully the information is there for you. So I know that if I'm trying to think in 5 dimensions about the 5-dimensional hypercube, I'm going to have 32 vertices, and so I can write them all out. For example, this is one of them, and then if I want to know what vertices are connected by an edge, well, this one would be connected, right? Because it differs only in one spot, and so on and so forth. This would also be connected. You get the picture. So this is sort of the logic of how to come up with the cube. An octahedron, these are going to be... Well, we'll just talk about the octahedron. It's really, like in 3 dimensions, you just, let's say this is x equals 1, and this is y equals 1, and this is z equals 1, and you just connect them like that. There's another word for this in the n-dimensional case. I believe it's called something crosstope or something. I forget exactly. So you can kind of, in your mind's eye, try to imagine some kind of weird 4-dimensional case where there's like 4 of these vertices and they're being connected, and it will be your analog of a 4-dimensional octahedron, which is called, I believe it's called a 16 cell. So, okay. So there's these canonical ways to construct the n-dimensional versions of these polytopes, right? We talked about cube octahedron. We've talked about the tetrahedron, or the n-dimensional simplex, it's called in the general case. And then I want to talk about these ones. So, and this, if I'm not making a mistake, and I think I'm right, there's something called the McKay correspondence, and that is where you have the connection from these Lie algebras to these n-dimensional polytopes. I'll briefly note, in case you're interested, in 4 dimensions, there's another regular polytope called F4. And the F4 symmetry in Lie theory is very interesting. And the F4, I'm calling it F4. That's not... Okay, in the world of the polytopes, you don't call it F4. It has F4 symmetry. It has many names. It's the hyperdiamond, it's the 24 cell. That's probably the most common name, but I don't think it's cool. I like hyperdiamond. It's got a bunch of other names. So there's this... It's like, if you're talking about the Platonic solids, but in the n-dimensional case, 4 dimensions is special. It has 6 of these. You could think of these as just being that there's 3 types, right? Because these, up to duality, right? There's 3 types. But then there's this 4th one, only in 4 dimensions. That's just incredible. And this is my favorite shape. It's just an amazing thing. It has beautiful symmetry, as if I could see it, right? But you can study it. You can study its shadows and everything. And so, but the thing is, this is not, in some sense, it's not fundamental. It is, basically, you can build it through, by combining a tesseract and a 4-dimensional analog of an octahedron. So a tesseract and a 16 cell can combine to form the 24 cell. And so, in a sense, it's not fundamental. And if, from a Lie theory point of view, the F4 symmetry looks something like this. And you have, but here you have 2 lines. And now trying to explain that this is not fundamental is a little more complicated, but I'll just say it has something to do. So you can argue that the ADE Lie groups or rather Lie algebras, Lie groups, whatever, are more fundamental because of a thing called Dynkin diagram folding. And so, while this is super interesting and probably important in physics in ways that we're still learning, it's... ask me in the comments if you want to know about the connection with physics. Very, very interesting, but outside the scope of this video. And so, while fascinating, in some ways not fundamental. Now, on the physics side, there might be a correspondence between this F4 symmetry and all the observables in quantum mechanics. So I find that absolutely incredible. But it's not the topic for today. And so with the McKay correspondence, there's a correspondence between E8 and, I'll write it here, E8 and E8 and this stuff, the icosahedral or dodecahedral symmetry. Okay. So, now, McKay, the way he describes, or when I look online and the way that this correspondence is described for E8, it's almost too obvious. I feel like there's something deeper, more interesting, and like more canonical that has to be found. Maybe people know it. Maybe, to great mathematicians, it's super obvious. But I don't know. The way that the McKay correspondence is actually described is a little bit... It's almost like too trivial to my taste. But anyway. So there's this correspondence. Okay. And so... now, I'll say that there's a theory of everything that has to do with E8. It's not super fleshed out. People have argued about it. And if it were just up to the scientific community, the physics community, I don't think the paper on it would have gotten much attention, honestly. But the thing is that the press picked up on this paper. It was written by someone, I think, out of UC Santa Barbara, kind of a surfer, maybe string theorist, deep theoretical physicist guy. And he just wrote this very speculative paper about E8. I think there was a mistake or two. But anyway, I'll just mention it because it's worth mentioning, that there is a lot of buzz in the popular world about a possible theory of everything related to E8. And in my personal opinion, I feel like this is pure speculation. I feel like there's a little too much going on with E8, but that there's something in the connection between the F4 symmetry and the E symmetries. So you have E6, E7, E8. There's something going on in the connection here where I think is the key to figuring everything out. Obviously, nobody knows yet exactly how these things work, or exactly how they're related to physics. Okay. Now, so I've been very interested in F4, the 24 cell, F4 as a Lie group and a Lie algebra, the ADE type, Dynkin diagram symmetries and all that stuff. And I've been interested in how, if I remember correctly, E6, E7, E8. So I think maybe I'm making a mistake. E6 is said to be the complexification of F4. Now it's very funny. Hold on, I'm gonna take a little sip. Hold on. What's the guy's name? Arnold. What's his first name? Is it Victor Arnold? Great mathematician. Gave a great lecture. And he says, well, if you talk to this mathematician and this mathematician, and he said the names, like these great mathematicians, he said, well, they will tell you that E6 is the complexification of F4. And I nod my head and pretend that I understand what that means. So if Arnold said that, then don't worry too much if you don't understand what is meant. But I think then, in a similar vein, E7 is thought to be the sort of the quaternionification, and E8 is thought to be sort of the octonionification of F4. Something weird like that. Okay? So these are connected in interesting ways. And you can see it if the McKay correspondence is to be taken seriously, and I think it is. You can see how F4 is embedded in the... Well, let's talk about four dimensions specifically, because that's the only place where F4 is existing in a polytope with the 24 cell. Now, interestingly, maybe this is why we live in a world of 4 dimensions. We have 3 dimensions of space, 1 of time. Maybe there's something special going on that happens only in 4 dimensions and nowhere, with nothing else. Ding, 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 right? That's interesting. Incidentally, I mean, it must have been a question old as time. Why do we live in a world of 3 dimensions of space and 1 of time? Physics doesn't really have an answer, right? And that's an awfully important question. It might have to do with knot theory, okay? Knot theory only works in a certain number of dimensions, and it might have to do with F4 symmetry. But it's both. These are interconnected, I'm quite sure. And Witten found this out in 1988. You can look it up. It made even I think it made Time magazine or something like that. 1988, Witten, knot theory. There's a correspondence with knot theory and quantum field theory. Okay, so let's go back to this. So, okay, so I'm very interested in, so let's talk about 4 dimensions. So we have F4, or rather, I'll say the 24 cell, but this has F4 symmetry, so I'll write that above it. And then we have it's called, oh gosh, there's a 600 cell, and there's I think it's a 120 cell. Hope I'm getting the numbers right. Again, up to duality, it's the same thing, okay? These are the analogs, the 4-dimensional analogs of the icosahedron and the dodecahedron. Now, I'm pretty sure you can, I don't like, I'm really afraid of making a mistake, so I'm always saying, I'm pretty sure, this is how my memory serves me. I'm pretty sure you can find the 24 cell embedded in here, or there's at least a way to construct it from the 24 cell, something like that. And so here, I think we have the E8 kind of symmetry in here. Now, what I want to talk about is the idea that, that, first of all, there's something that I consider sort of the canonical rotation in 3 dimensions, which is, you can get it from a dodecahedron. So, and I'll say what it is first, and then I'll explain why I'm thinking of it this way. I wish I could draw a dodecahedron, but inside of a dodecahedron, you can embed 5 cubes. Okay, this is well known. And so you have 5 cubes inside a dodecahedron. This gives you a way to sort of rotate the cube and then come back around. Okay? And on one of the faces, well, the faces are pentagons. So if you imagine it flat on a table, you have this dodecahedron flat on a table, and it's, the surface that is in contact with the table is a pentagon. Well, there's sort of this dual pentagon here. If I can draw it, I'll draw these little dots like this, I think. Sort of dual. I'm not drawing it well, obviously. But there's this notion of a dual pentagon. So even though we have a dodecahedron where the dual, normally we talk about it as an icosahedron, there's this other, quote-unquote dual, which is really just a reflection. All we've done here is reflected. But we could reflect in many different ways, right? So it's sort of interesting. So there's this this idea of this dual, and this is hard for me to explain, by the way, so I'm going to struggle to explain the stuff I want to talk about. So there's this canonical way to rotate that is indicated by the dodecahedron, because we start with 1 cube, and there's these 5 cubes embedded inside. So if we talked about a vector that was in the middle of the dodecahedron, and it points to the center of a cube, and then you go to the next cube, and you go to the next cube, and you go to the next cube, and the next cube, it does this interesting rotation. And I'm not sure exactly how to calculate that rotation in the neatest way possible. If anyone can figure that out, or they know, leave a comment. It's not too hard of a geometry problem, but it's on my list of things to do. Well, then you could look at this sort of quote-unquote dual, which is just a reflection, but this quote-unquote dual, and you could get a different rotation, which I think just it's a different rotation. So you have these 2 rotations, sort of what I'll call canonical rotations that are encoded in the dodecahedron. Now, I'm thinking of it that way, and I obviously don't have to, but I was thinking of a problem maybe 6 years ago or something, and this, for me, when I found out that you can embed 5 cubes inside of a dodecahedron, I realized this is the answer to a problem I thought about like 6 years ago. And I was very interested in this problem for the math side of it, but it has a practical way of explaining this problem. So imagine you are YouTube, and people upload movies, full-on like Hollywood movies, and you want to automatically detect them and to, give it the copyright violation or whatever. So the problem you have is people slightly distort the movie and then upload it. So you can't just check for an automatic match, right? So suppose, for example, people are rotating the movie. People might even just put it upside down and just say, yeah, just flip your phone upside down and watch, So you want to deal with all the possible rotations, and you want to be able to figure out if they used the movie. Now, I'm sure Google has figured this out. Now, have they figured it out in the best possible way? I don't know. Like, we've had, is it 254 encoding that we've had for a long time? And now there's 255, which apparently uses better algorithms. So even with something as broad and important as video encoding, there's new algorithms. I might be getting the numbers wrong, but the new one, I guess, is a patent. So that's kind of evil to me, but that's another story. But so, is YouTube answering this question in the best way possible? They're probably using AI. But anyway, suppose that they weren't, that they needed an algorithm. Maybe they are, maybe they aren't. I'm sure they've thought about this problem, obviously. But so I thought, well, here's an idea. You take the screen of the picture of the video. Now you're analyzing it frame by frame. What you do is you put it on the surface of a sphere, okay? Just sort of wrap it on the surface of a sphere, and then you do random rotations and take random paths going through, right? So random rotations of the sphere, and or equivalently, you just do random paths on the surface of the sphere, and it will sort of cut through here randomly, right? That's the idea. To come up with some kind of random way of sampling the data where it doesn't matter that it's been rotated in any way. Do you see? So then that gives you an interesting question. What exactly, or how many different ways can you come up with to do a random rotation of the sphere? And what does that mean? That's an interesting question. It's kind of like a random walk on a sphere kind of thing. But right now as I'm saying this, I mean, you can sort of embed this in the space of quaternions, or the unit algebra of quaternions or whatever, which we write like this, quaternions. And you can do it with that kind of thing. It's equivalent to just looking at rotations. But this is a kind of thing I was looking at, and I was wondering, is there a canonical rotation? Right? Meaning, is there, like, we can talk about all kinds of random rotations, but is there one rotation that is, in some sense, more special? And I don't mean like a specific rotation, because if you just have, let's say, here's your identity, and you pick a rotation, and you just keep applying that rotation, it's always going to be a great circle, or it's just going to rotate around like normal. But we're talking about sort of rotating the axis of rotation, that kind of thing. So we're rotating, and we're rotating the axis at the same time, and maybe we're rotating that. So it's like you have a derivative and a second derivative and a third derivative ad infinitum, and what does it look like? Or do you have, in rotation you have 3 degrees of freedom, so like I, j, k. But again, if you just combine those, so we have equal amounts of I, j, and k, that will just be one great circle. So the answer must be, I think it's what I kind of said. You have a derivative, a second derivative, a third derivative ad infinitum, and then you're doing some kind of rotation within that space. It's sort of strange. You get all kinds of weird spirals. It's like polar form, but in 3 dimensions. Well, the surface of a circle is 2 dimensions, obviously. So it's weird. It's a weird question. It's maybe it's equivalent to some kind of question about a spiral on a plane. And studying spirals is super interesting to me, and sort of related to Mobius transformations. And I think people need to study spirals more. There's logarithmic spirals. There's a bunch of types of spirals, so it might be sort of related to that. And I'm thinking of rotation as being represented by moving around this, or rotating the sphere, and you have an axis of rotation that moves around. But so you kind of can think of it as there being a point at infinity on this on the spiral. Yada yada yada, all kinds of stuff like that. So I just had this question and I didn't have the answer. Is there a canonical rotation or something? And now I don't know that the answer is this stuff with the dodecahedron, but it's at least a potential answer. That's the first time I jumped out of my seat when I saw this. It was only a few months ago or something. I was like, my God, you can fit 5 cubes inside of a dodecahedron. That's the canonical rotation. Okay, so maybe I'm being a little silly, maybe not. Let me know what you think in the comments. Okay, but this, anytime you have a pentagon or a dodecahedron or anything like that, you have the golden ratio everywhere, okay? And the golden ratio, we'll call it phi, because that's what it's called. I'm bad at writing phi. You could write it like that. Okay, and incidentally, there's also a golden spiral, which is a special case of the logarithmic spirals. So, interesting. It's a unique spiral in the large family of logarithmic spirals. So, however, this is inside the pentagon, and I've almost just taken people's word for it. I don't even know, but it's probably like the ratio of this to this or something, to one of the sides. I don't even really know, but it's everywhere. When you start talking about regular pentagons or dodecahedrons, the golden ratio appears everywhere. If you learn how to construct the n-dimensional analog of well, let's just talk about 4 dimensions. The 120 cell or the 600 cell, you can look at the ways to construct them, and it will have phi in there. So let me see. No, I don't want to bring it up, actually. Let me try to bring it up for you so you can see how it's constructed. There's one website that's really good. It's this Qbox Info here. Sorry it's so bright. And actually, I'm more interested in the 120 cell, which is of the dodecahedron. But let's just look at this first. Sorry it's too small, but here's the coordinates, so a way to construct it. Coordinates of the 600 cell are all permutations of coordinates and changes of sign of the point 1111 2000. This might be similar to constructing a 24 cell. That looks very similar to a 24 cell, but maybe it's different. And all even permutations and all changes of sign of phi 1. This is 1 over phi 0. Okay, so, and isn't 1 over phi, is that root 5 minus 1 over 2? There's some interesting special relationship between phi and 1 over phi. And probably, while I'm on that topic, it probably has something to do with, there's something interesting going on where, let's say you're talking about tiling space, and obviously, or tiling 2D space. Obviously, you can't tile it with pentagons. You could tile it with triangles, squares, or hexagons. But what you can do is, let's see, let's connect these. let's connect all the ones that are not adjacent, but off by 1 or whatever. So we get this kind of gram. But within it there's another pentagon here inside. Do you see that? And it's the dual, what I earlier called this dual pentagon. I'll highlight it with the color just in case some of you don't see it. There's a pentagon in here. And so while you cannot tile space in the normal sense, you can sort of do this zooming in and zooming out tiling. There'll be another one like really big up here or something, you know. And I mean, because you can repeat this process, right, and go even further. Obviously, if I learn how to draw, which I don't know how, there's allegedly another pentagon in here. So that's not exactly tiling, but it's sort of reminiscent. And so is there some connection to phi and this 1 over phi here? There's got to be some connection there. There's got to be some connection. I don't know. Okay. Now, let's talk about the 120 cell, which is what I originally wanted to talk about, because that's the analog, 4-dimensional analog of the dodecahedron. And, oh gosh, construction's kind of crazy. Anyway, there's phi all over the place. Okay, that's what I wanted to point out. Done. QED. And so, if you want to go to where the whole point, what I wanted to talk about, you need to, well, we accept, okay, so this idea of a canonical rotation may be controversial. You can disagree with it, whatever. Just go along for the ride with me here. Let's just call it the canonical rotation. This idea of embedding cubes inside of a dodecahedron. And you can also embed hypercubes inside of the 120 cell, I believe. So you can increase this story to n-dimensional case of embedding inside and getting sort of canonical rotations. And so another thing that I'm interested in is the relationship between, let's say, n-dimensional space and n+1 dimensional space, right? Just to whet a person's appetite. Like, how do you go from a circle to a sphere? Obviously, this is a circle on the left and a sphere on the right. I mean, anyone can see that. But is there like a canonical method to do that? Well, one idea is, okay, you have a circle, okay? And now, imagine it's like a pancake, okay? And you make 2 copies of it, and then, so they're sitting on top of each other, 2 copies, and you stick in your air pump, and you pump air in the middle. And so it becomes 2 pancakes, but there's air in the middle. And eventually you blow it up completely, and it is a full-on sphere. And so you have this circle that was stretched on top and a circle that was stretched on bottom, right? So this is a way to kind of try to construct a 3-dimensional object from a 2-dimensional object. So I'm interested in these kinds of ideas and constructions and what happens. There's all kinds of things to ask, especially talking about hyperspheres. You know, what happens with the areas of the surfaces and the volumes and all this kinds of stuff. Surface area, volume. What happens, obviously we have these famous formulas, pi r squared. And is it 4/3 pi r cubed? I think is the volume of a sphere, right? Well, what's the formula for the surface area of a sphere, and how does it relate to the area of a circle? Well, interesting questions to ask. And then we want to think about the n-dimensional case. If you have a 5-dimensional sphere and a 4-dimensional sphere, what connections are there between the formulas for the hypervolume? And I hope you get the idea. These kinds of things are interesting questions. And so if we have some kind of canonical way to iterate dimensions is very important. And somehow this number phi is connected to all of this. Okay? Here's the speculation. And again, I'll quote. And there's another quote in this book. It's not just this one. It comes up. There's a few quotes that I wanted to find, but I only found one. It says, McKay and Thompson conjectured the existence of a natural infinite dimensional representation of the monster. So E8... Oh, I accidentally did something here. Is it gonna... There. Oh my god, no. No. Okay. E8 related to... What do you call it? The n-dimensional dodecahedron. I don't know what you call it. N-dimensional dodecahedron. Or icosahedron. Same symmetry groups, okay? These are connected. And this is connected with the monster somehow. Pretty sure. Again, if I got that wrong, this whole conversation is stupid. And if you're along for the ride with me, somehow the canonical rotation in n dimensions okay, so here's the thing. You study all these symmetry groups. There are symmetries that must cross dimensions, right? Somehow a three-dimensional symmetry... Now, there's probably so many different things that you could look at. And basically you can look at embedded objects, like embedding two-dimensional surfaces into three-dimensional space, embedding three-dimensional surfaces, we call them manifolds, into four-dimensional space, right? There's all kinds of ways to look at that. But also to look at it from sort of a group theoretic point of view. Maybe look from like an ADE kind of point of view. And there should be more information out there about symmetries that go from one dimension to another. Again, this is speculation for me. Maybe this is well understood for professional mathematicians. I'm not one. But, and the word transcend comes to mind, but I don't want to use it really, like transcending dimension, because it sounds like you're going above dimension. That's not what well, transcending the dimension that you're in. So let's try to get a little more concrete. Still, it's not going to be rigorous, but we can maybe talk about, say, the golden spiral or various logarithmic spirals. You kind of think of it... actually, let's talk about an Archimedean spiral. So I think if you do just an R equals theta equation, does that give you Archimedean? Basically, it spirals and these distances are the same. Here to here, same. It increases linearly. So let's see, so it goes around once. If it's r equals theta, isn't this 2 pi? Right? And it goes around again. This would be another 2 pi. So if it went again, 2 pi. All right, I think that works. So that's an Archimedean spiral, if I'm saying it correctly. And so imagine at the point at infinity, if it off at the point at infinity, and if that sounds like hocus pocus to you, look up about Riemann spheres, okay? And maybe projective geometry, but at the point at infinity, if the spiral connected back to the beginning, that's sort of interesting. And you can then generalize that to the logarithmic case as well. I like to imagine a spiral going off to infinity and connecting back. And we're going to get even... There's even other things to connect this with that I feel should be connected, but I don't have the rigorous connection for you, so it's speculation. I'm sorry. We're going to talk about earthquakes. There's something called Omori's Law. And I think in Japanese, sometimes you might see a line over here. It's a long vowel. It's not important. Omori's Law is basically that suppose there's a magnitude 6 earthquake nearby, and you're wondering, well, what's the probability of another big earthquake, right? It's obviously much higher now compared to an ordinary day. You know, right after a big earthquake, there's a higher chance of another one. And basically, Omori's Law is that the idea that this declines by... It's an inverse squared law. Something times some constant. An inverse squared law. So that's Omori's Law. Now, this can't be true forever because it means that if it were true forever, then once you get a year away from that magnitude 6 earthquake, there's like no chance of another earthquake, and you go further and further into the future, and eventually the probability goes to 0 that there's going to be an earthquake. I say that, but I'm thinking I'm not sure. So it's complicated, but I imagine that there's another competing law. I don't know what it's called, but it's basically the idea that you become overdue for an earthquake, right? If it's been 100 years and there's been no major earthquake, let's say you're in Japan, where there's a lot of earthquakes, and in your area it's been 100 years without a big one. Well, you're sort of overdue, right? I'll call it the overdue law. Maybe there's a name. So these are... I have this... Maybe I'll study this properly. I've barely studied it at all. I've recently become a little bit interested in earthquakes since I'm in Japan and all. And so in my head, there's some kind of competition between two laws. This one I know is a real thing. This one I'm being hand wavy, but it's got to be a thing, right? You hear seismologists kind of talk in those terms. But they're looking at the plate tectonics, how things are actually moving. So there's some kind of fundamental movement, impetus going on that breaks Omori's Law. And so what are the dynamics? How do these interact? Or like, what's the full theory here? How do we reconcile these two contradicting notions? And I'm reminded again of a different thing, which is the financial markets. So let's say you have some stock, or the stock market overall, and you have all these weird, seemingly random movements, right, in the stock market. You might call them random walks. But I got to take a sip. However, let's take the United States stock market. Historically, it's gone up on average. So you can imagine there's something probably similar to Omori's Law, where you have, let's say you had ordinary motion, and then suddenly, boom, high volatility, right? And then maybe it tapers off. This kind of thing happens in the stock market. A period of high volatility. Now, in the world of the options market, apparently, before, I think, 1987, before there was it Black Monday or Black Tuesday? There was this day I'm pretty sure it was 1987, October 1987. The stock market crashed like 20% or something in a day, on a Monday, I think, Monday or Tuesday. Now, before that, when people were pricing options, supposedly, what I read is that they used to use a bell curve, standard normal distribution. Is it also called a Gaussian? Yeah, right? The Gaussian curve. Now, that is inappropriate for stocks, because if you had a random variable with constant volatility, then the normal distribution might be appropriate. But in the stock market, volatility changes. Volatility is also a variable, which means that the tails must be thicker. There's in these distributions, there's something called kurtosis, if you want to learn more about it. It has something to do with something in here about the thickness of the tails, kurtosis. But basically, I don't remember exactly. Kurtosis might just have to do with the spread of... I just don't remember, I'm sorry. But the idea is that the tails need to be thicker, that a normal distribution is not appropriate. Now, the guy who came up... his name is Mandelbrot. I was going to say the guy who came up with the Mandelbrot set. Mandelbrot. Obviously, sort of pioneer in studying fractals. He, in the early days... Did he actually print out... Was he the first to print out pictures of the Mandelbrot set calculated by computer? Maybe. Not totally sure, but... Well, Mandelbrot is famous for his work on the Mandelbrot set. I'm pretty sure about that. Anyway, he had a book that I read good 20 years ago or something. And he talks about financial markets at some point. And the story of fractals is probably relevant here. That if you have variation, let's say you have volatility as a variable. I think usually it's called vega, but I don't know how to write vega. But anyways, normally in the options world it's called vega. So volatility as a variable. And if that is varying, if that itself is taking something of a random walk, then he was arguing, I think, that you have something that's it's fractal-like behavior, meaning that you could zoom in on any part of this, and like if I zoomed in on this box, I would see, well, it's going down in this particular case. So let's zoom in right here. Then I would see something that resembles a larger picture. In other words, if I give you some chart of a stock and I ask you, what's the time scale? Are these years? Are they seconds? What is that? You have no idea, right? That's the idea. It's fractalesque, right? So I think that's very interesting. Now, I think here maybe we need that there's Mandelbrot's law, and then there's the fundamental laws competing, because the stock market is based on real phenomena. You cannot just have volatility that just goes off to the moon. All right, volatility has some limits in how much, where it can go. That because stock markets, financial markets are also ultimately reflecting reality in some way. So I think it's a similar situation. You have some competing laws here. Okay, so first of all, I find all of this very interesting in its own right. And this fractalesque random walk, can we bring this conversation to the world of these spirals, logarithmic spirals, and sort of Mobius transformations? You can imagine a Mobius transformation as a sphere. So many topics. Okay, we've got a complex plane. The complex plane, sometimes called the Argand plane. If you studied complex numbers in high school, you studied it, the complex plane. You can imagine a Riemann sphere on top of the complex plane. Basically, when you study complex functions, you have some function z. Okay, z is a complex number. And a way to imagine this is on a Riemann sphere. Or you use a Riemann sphere as a tool. And in particular, the Mobius transformations are of this form. And my brain's getting a little tired. I don't remember well, yeah, I don't remember the best explanation here. I believe, if I recall correctly, the Mobius transformations are keeping something... They're conformal transformations. They're keeping something conserved. And... yeah, so there's special types of complex functions, right? Hope I'm not making any mistakes in what I'm saying. But basically, you can imagine them as the Riemann sphere. They're rigid body transformations of the Riemann sphere. Mobius transformations are rigid body transformations, which means a rigid body transformation is the linear transformations. They're sort of the affine transformations. They're the ordinary linear transformations plus translations. Transformations of the Riemann sphere. I'm getting lazy to write it. This is a really amazing fact. Great fact. One of my favorite facts. Mobius transformations are equivalent to, rigid body transformations of the Riemann sphere. So you can imagine the Riemann sphere and you move it around, okay? And you get a Mobius transformation. So there's a one-to-one correspondence, one-to-one mapping between rigid body transformations of the Riemann sphere and Mobius transformations. So, I mean, scaling acts as just taking the sphere and lifting it up, or shrinking it, I guess, or just moving it down. Well, I don't know how that works. I have to think about it. So, trying to get back to the story of, in the previous slide, of rotating, like, what is the canonical rotation, and if you have people uploading videos, how do you rotate in a random way? Like, what I want is, there's a canonical rotation. Let's use the stock market as an example. Suppose the stock market goes up. We're talking about the American stock market. Let's say on average, it goes up by 8%. So this is the fundamental law that we talked about. On average, up 8% per year. Then we have the Mandelbrot law, fractal-esque variation, and they're sort of competing in some sense. That's weird. How do we reconcile that? I don't know. Somebody become a mathematician and figure that out for us. And so I want to draw a correspondence between this stock market theory and Mobius transformations, where the average, so this average 8% incline, okay, let's say it's like that, is like a Mobius transformation. But let's say you've got a bunch of Mobius transformations. In some way, so we're talking about rigid body transformations. You can imagine you do a random walk of the Riemann sphere, right? And it has this fractalesque component to it. But the average, the competing law here is the average. God, this is a heck of a rant. What are we talking about? No, but this is cool. The average is the equivalence of the canonical rotation. That's our guiding, our North Star. You have a canonical rotation, and then you allow for fractalesque perturbations around the canonical rotation. And maybe there's maybe two of them, like we talked about earlier. Sort of quote-unquote duals. So, what the heck are we talking about? What is going on? There's also, getting even crazier, John Baez. and the rolling ball is a discussion of octonions. It is a model for talking about the algebra of octonions. And so there's a paper. If you Google this, you'll find the paper. This is connected with E6, E7, E8. See if I can bring up the paper here for us. Huh? Why not? John Baez, rolling ball. I'm pretty sure it's going to come up. So there are videos as well. Great stuff. G2 and the rolling ball. So G2 is the automorphism group of the octonions. Basically telling you more or less how octonions transform into other octonions. And maybe actually there's a better paper for making sense of this. This is very specific. He actually just has, well, there's some interesting, well, it's all very interesting, but for the non-practicing mathematician, there are a lot of interesting things here. And the history here, very interesting. But he also has a overall paper about octonions. Just search for John Baez and octonions. His sort of a, what do you call it, a review paper? A survey paper. And it's very good. And the rolling ball, we were talking about rigid body transformations of the Riemann sphere. Mobius transformations. Well, those are complex functions. So when you're talking about octonions, and if you want to understand octonions, there's the Cayley-Dickson process. Good Lord. You start with I. You have A plus BI. Then you say that we have some amount of, let's call it C and D. You have some amount of that, and then you have some amount of this new thing. Am I doing this correctly? I think I'm doing it wrong. I think what we want to do is inside of I, we put a new thing. So A plus B times some new thing. I forget. It's a Cayley-Dickson process. I'm too tired. I'm sorry. But it allows you to go from real numbers to complex numbers to the quaternions to octonians and further. ... Sedenians are next. But this RHCO comes up a lot. They're important for certain reasons. And what I want to say is that the Mobius transformations are, they're isomorphic to the quaternion algebra. I'll write it as what's really spin 3. So SO3 is the double cover of SU2, which I believe is, I think it's isomorphic, if I'm not making a silly mistake, to spin 3. Now, so and this is isomorphic to Mobius transformations. In fact, I think maybe Mobius transformations, I think you can write as the automorphism group of complex numbers. Is that correct? That's kind of getting back to thinking of them as, complex functions. But I kind of forget. But then what about when you go to octonions? Well, I think what you might want to think about imagining is this rolling... What the heck just happened? This rolling Riemann sphere rolling on another Riemann sphere. Weird, huh? Very weird. And this is what I mean is the rolling ball that John Baez is talking about. So I knew about the rolling ball, about his paper, and I was thinking very deeply. I love Mobius transformations and SU2 and SO3 and spin 3, spinners, all that exciting stuff. Connects to the Lorentz group of special relativity. It's just incredible. Very interesting. But I was trying to think, how do I understand octonions? Because octonions are probably the key to understanding the future of physics, I think. Many people think that. But it's a whole other level of complexity above this stuff. Like, if you think Mobius transformations are complicated, octonions are like an order of magnitude more complicated. Maybe, right? Something like that. It's a level above. And I can't remember all the stuff I was thinking, but I was thinking on very intuitive, very geometric levels. I was thinking very intuitively and geometrically, and I had forgotten about the rolling ball stuff, but I was imagining sort of this Riemann spheres sort of rotating on top of each other. This to me was the answer that I was looking for. And I was thinking about this for a while, and then I realized, my God, it's the rolling ball. So it's the opposite of easy to understand, but the rolling ball might be the key to understanding about sort of octonions interacting with octonions, right? Multiplying times each other, transformations of octonions, the automorphism group of octonions. To gain some kind of intuitive understanding of this. Some people are happy with an algebraic understanding. I'll never understand those people. I don't think that's intuitive. That because the intuitive understanding allows you to understand things on a deeper level, that allows you to connect it with other areas, to understand its place in the world of math. And yeah, I think intuitive understanding is extremely important. Like, I was talking with someone about SU3, and I was explaining how eventually I came up with an intuitive way to try to understand SU3. And they said, "Oh, I'm not interested in that. It's just 3x3 complex matrices, whatever." So they said, the algebra is that. So who cares? Which SU3 corresponds to the symmetry group of the strong force. So very important group. And anyway, the rolling ball, excellent way to try to understand octonions. Absolutely fantastic. And I'm thinking of this rolling ball as the Riemann sphere, a Riemann sphere rolling around on another Riemann sphere. And you get some weird things, because when a ball rolls on another ball, like we're imagining it's not sliding on the ball. So you get, like, you can come back around to the same spot, but the ball that's rolling has changed its orientation, right? But there's certain ways that you can do that, right? So that's where it gets it has a structure. And I think that is also key to understand, well, it's related to the non-associativity of the octonions for sure. Something in there. There's a lot of stuff to think about. But I just wanted to say, because I think Baez talks about the rolling ball. I don't think he's thinking of the Riemann sphere. And I'm being a bit hand-wavy, to be fair. Absolutely. I'm being very hand-wavy. But I'm thinking rolling ball, and I'm trying to think of a Riemann sphere on another Riemann sphere. It's a little weird and hard to understand. But when you're rotating these Riemann spheres, when you're rolling them, when you're rolling one on the other, like I can say I start on the North Pole. I can roll a little bit here, a little bit over here. Like let's say like straight south. I take a 90-degree turn. I take another 90-degree turn and up. Now, so it's this little triangle. If I went all the way down to the equator and then over and then 90-degree turn up here, all of these are 90 degrees. It adds up to 270 degrees, right? It's the curvature of the sphere. So this is Riemannian geometry. The big triangle here is going to have much more than 180 degrees, right? On a flat space, triangles have angles that add up to 180 degrees. On the surface of a sphere, they add up to more than 180 degrees, and the bigger the triangle is, the bigger that number is going to be. So if you look at little small triangles around the North Pole, it will rotate less and less. And so imagine we're at the North Pole. I don't know why I drew a line. We're at the North Pole, and I want to rotate just a little bit. So I make a little journey going down and back. Or I want to rotate a lot, so I make a big journey, right? And so somehow this corresponds to the story of spirals and this sort of random walk, because I can roll around. Let's say I pick some kind of random number, maybe a random number between this 90-degree rotation journey and a smaller one and 0, somewhere between 0 and the equator, and then I just come back in the way I've said, and I do a bunch of these. It's like rotating myself in a two-dimensional way right now. Well, it's not just two-dimensional, right? What's going on here? I don't know. This is a ramble. But the way that this ball rolls on another ball is interesting. It's of interest. And doing it sort of randomly. Now, spirals are related to Mobius transformations, okay? You have these loxodromes, or, yeah, I'll call them loxodromes. So the loxodrome will be like a straight line. So suppose you're on the surface of the Earth, and if you just go straight, that's going to be a great circle. But if you want to go in a path that maintains constant heading on your compass, right? You have to continually and constantly adjust your heading to maintain the angle between your velocity direction and the North Pole, for example. You want to keep that angle constant. Well, on the I believe on the Mercator projection, it'll just be a straight line, right? It's constant angle. So this is the North Pole. You're keeping it constant. So it's a straight line. But it's a loxodrome, I'm calling it. So you could take this, and if it were on the sphere, okay, on the sphere it's going to look, I don't know. It's going to look something like this. Kind of go around and... not that steeply, I don't know. Something like this. But you don't go, well, you go around the North Pole infinitely, but in finite time. Interesting, huh? But when you sort of unwrap the globe onto the Mercator projection, it's a straight line. It's called a rhumb line. Sometimes I use the French. I call it a loxodrome or loxodromie. I don't really like calling it a rhumb line because it's just a name or something, right? I don't know. It doesn't mean anything. Anyway, so there's something, one of the Mobius transformations sort of decompose into, I think it's 4, they're compositions of 4 sort of fundamental types of transformations. There's parabolic transformation, and there's a scaling one. And there's probably one other. And then there's the really interesting one is loxodromic transformation. And what I'm thinking is, instead of this straight line, maybe something like a sinusoid. Now, this would not be a Mobius transformation now. It would be something else. Perhaps you could describe this in terms of octonions. And perhaps, alternatively, maybe it is of interest that we have something like the Mandelbrot discussion, where we have sort of something like this, but like the earthquake being overdue, or the fact that the stock market isn't pure randomness, it has to come back to reality. Something like this. And I feel like this is really hard to connect all these disparate things. But I think this is sort of the icing on the cake. Mobius transformation, but sort of generalize it into more of an octonionic sense. This is connected with the stock market discussion and the discussion of earthquakes that I've had before. You have something of a spiral, but it's varying, and there's maybe a fractal component here. Very strange, very weird. And somehow this relates, I believe, to a story of canonical rotations. So how do we do that? Well, here's one way. Take that, what I called the canonical rotation, and apply it to the Mobius sphere. You'll get a canonical, you'll get some kind of, I need to do this. I don't know what it looks like. I don't know what it looks like. Apply the canonical rotation. Will you get a this kind of run line? I don't know. I really need to figure this out. But this is good that I'm making this video, because it's making me think of ideas here to further develop this. Do you get a run line? I really don't know. So again, in case it's not clear, the rotation that you get from the cubes that are embedded in the dodecahedron, 5 cubes inside a dodecahedron, to me, it describes a rotation. This rotation that's being described probably has to do something with the number phi, the golden ratio, because golden ratio is all over the place with those dodecahedrons. And there's probably an n-dimensional version of this, because you can do the same thing, I'm pretty sure, for the 4-dimensional hypercube and the 4-dimensional dodecahedron, the n-dimensional hypercube and the n-dimensional dodecahedron. You get some kind of canonical rotation. And maybe, sometimes in math, you only need to have something understood at level 2 or level 3, and then you have it for n dimensions, or the level n case. And so maybe when we have RHCO I talked about earlier, RCHO rather, this is, there's a few ways of saying it, but they're the invertible division algebras, is that it? And once you get to the next one is the Sedenians, and it becomes non-invertible, meaning yeah, I'm not going to explain it right now. Non-invertible. So in other words, if you multiplied 2 Sedenians together and you got 0, and you told me, hey, I multiplied 2 Sedenians together and I got 0, that doesn't tell me what the Sedenians were. I guess that's true with others, because but the difference is you can multiply two non-zero Sedenians and get 0. It's weird. So what happens is, as you do this Cayley-Dixon process, you gain power in a sense, right? The Octonians have powers that the Quaternions don't have, and the Quaternions have powers, abilities, there's structure, additional structure that complex numbers don't have, and yada yada yada, right? But as you sort of gain power, you become more general. And by becoming more general, you lose properties. Each step, you lose properties. So from real to complex, you lose the property of being well-ordered in a canonical sense. When you move from complex to quaternionic, you lose the commutativity property. When you go from quaternions to octonians, you lose associativity. There's this weaker form of associativity. Is it called alternative associativity? Something like that. But the ordinary associativity breaks down. And when you go to the Sedenians, okay, then you lose invertibility. In other words, you lose, if it's applicable to physics, you lose information, actually, in a physics context. That's why physicists, they really don't like non-invertible stuff. If stuff is invertible, it's sort of deterministic. So that's actually interesting because, quantum mechanics is sort of fundamentally not deterministic. In a sense, if you view it from a many worlds theory point of view, or many worlds hypothesis, or rather many worlds interpretation point of view, you can argue that it is deterministic, I think. But, at face value, quantum mechanics is non-deterministic. So that probably is related to this stuff in interesting ways. If you're kind of scratching your head and saying, what the heck does this have anything to do with physics? Look up Cole Furry. She explains this stuff quite well. Or Baez. John Baez, Cole Furry. There's others. So we want to go from Mobius transformations to the world of octonians, and I think that instead of just being limited to loxodromic transformations, maybe we need the rolling ball, which may allow for these more complicated sort of lines that are they're no longer just loxodromies or rum lines. They're more complicated, maybe a little bit fractalesque. And I tend to think that there's sort of scaling invariance. I mean, reality might be scale invariant. That's sort of a crazy thing to think about, in some sense. Now I'm getting into real speculation. That's serious speculation. But I mean, physicists talk about something from nothing, the idea of the Big Bang happening ultimately from, if you have fluctuations of the fields of, the quantum fields of nature, and you're given near infinite time. So let's suppose that our universe in the end becomes sort of cold. All the energy is spread out everywhere, and it's just very cold and nothing's really happening. But you could argue, I suppose, that given infinite, basically infinite time of this cold nothingness, the quantum fluctuations would eventually, given enough time, randomly basically create a new universe, a Big Bang, with cosmic inflation and all this kind of stuff. I'm not arguing that. Physicists argue that. Or something close to it. Something from nothing is the idea. And it's an interesting idea. Maybe things are kind of scale invariant. We definitely have in special relativity that distance is non-absolute. Is there anything else I want to say? I haven't really done a proper job of explaining the thing. I believe that looking at these canonical n-dimensional rotations, in we're talking n-dimensional here. We're not talking about any specific number of dimensions. That this might be an important part of an understanding octonion, how octonions sort of interact or multiply via the rolling ball, via the generalization of loxodromic transformations. And this might be... I had it for a second. There's something I wanted to say. If you've made it this far, bravo. First of all, I mean, the octonions and all this stuff might be the key to understanding, sort of solving some of the biggest problems in physics, right? The reconciling gravity with quantum physics. Figuring out if something in string theory is actually of any real physical use, or actually physically explains anything. But I think the octonions are the best unification candidate out there. Or this, even, I'm interested also in the Sedenians. There's a paper came out of Wuhan, China, actually. Sedenians. If you look up Sedenians and unification, you might find it. And, I think someone like Leonard Susskind would be very much against it, because Leonard Susskind believes in what he calls the zeroth law of physics, the conservation of information. Now, I think the Sedenians might be interesting if you, for some reason, believe that information is not conserved, which you might arrive at that conclusion from some kind of many worlds interpretation view on things. Yes, E8. So I believe there's something here, something out there about iterating from one dimension to the next, possibly from a sort of an ADE theoretic point of view. And I believed that E8 encodes this kind of, there's some kind of symmetry that transcends from one dimension to the next. Right? I mean, the on a basic level, the story that I explained about the two circles and you inflate them to make a sphere, going from 2 dimensions to 3 dimensions, there's already a symmetry here. There's the northern hemisphere and the southern hemisphere. That's on a very basic level. But there's the Hopf fibration is something where it interconnects 3 dimensions and 4 dimensions. And so that's what I think. There's something going on where E8, and I believe this, and I wouldn't, make this rambling video, except that this book talks about it, the book that I brought up. That there's E8 is telling us something about, supposedly there's an existence of a natural infinite dimensional representation of the monster, and somehow the monster is connected with E8. So again, I wouldn't have said all this stuff because it's very hand wavy. But because they're talking about it in this book, I said to myself, well, I think there's something there. And now maybe it's well understood by certain individuals, but this is very advanced math. So if it is understood, I don't think a lot of people know about it, but it might be entirely well understood in certain papers. And good. If that's the case, I'm very happy. I want to learn about it. I don't care about... I'm not saying I came up with this. Much smarter people have figured out a lot more about this and know a lot more about this than I do. That's not the point. I have an intuition, an idea, and I feel that it has been, by what I've read in this book, I feel it's been confirmed as an interesting idea. That's all. And yeah, this is not about me. I'm just genuinely interested in this stuff, and if anyone has more information, by all means, let me know in the comments. And yeah, I'm left with this nagging feeling from what I've studied of Lie theory and Coxeter systems and lattices. I feel like nobody's talking enough about the connections from dimension n to n plus 1. There's got to be more going on there. Now, maybe it's very well understood, the Hopf vibration, yada yada. But maybe there's stuff that we don't quite understand. And this book, by the way, is from 1988. 1 year after I was born. So I'm sure there's been a lot of new developments. But anyway, I find this interesting. Really, is there a connection between what I'm calling the canonical rotation, which is sort of encoded in the dodecahedron? Is there a connection between that and these spirals and octonions and maybe E8 and the monster? That's a huge and very interesting question. And the connections between E8 and the monster are definitely interesting, and there's more stuff. There's the Golay, or is it pronounced Golai code, the Leech lattice, and these other things. And also E8 and the dodecahedron, the n-dimensional dodecahedron. That, again, it's the McKay correspondence, and unfortunately, when you look this stuff up, you find yourself swimming up to your neck in string theory, because it's the string theorists who are talking about this stuff mainly. And that's unfortunate, because I don't think it forcefully needs to have anything to do with string theory. But it happens to be that string theorists are interested in it, so that's what you get. And so I feel, and like there's this ADS CFT correspondence. CFT being conformal field theory, relating. The Mobius transformations are conformal transformations, so it's sort of connected in there. But the ADS CFT correspondence, correspondence is also, that comes out of string theory. So that and McKay correspondence, unfortunately, I'm like, I need to learn string theory so I can understand what these people are saying. And also quiver theory, which quiver theory is just undirected. Quivers are undirected graphs. So it's like most of graph theory is, that I've seen, all of it was... Sorry, I said that backwards. Most of graph theory is all undirected graphs. Quivers are directed graphs. And quivers don't forcefully have to do anything with string theory, but see, it comes from the Dynkin diagrams that people are interested in quivers. Because they're basically directed graphs. And, yeah. So ADE stuff, there's all kinds of stuff to look at with ADE, relating it to combinatorics, and there's got to be some stuff there with graph theory. But I've never seen it by picking up a graph theory book, unfortunately. But I mean, Dynkin diagrams are essentially graphs. So anyway, I think that's enough. I think I've generally kind of said what I wanted to say, and it's a journey. I love it. It's crazy. A lot of this is a lot of speculation, and people might attack, but I think it's important to keep in mind that for me, pseudoscience is people who make unsubstantiated claims without humility, without saying this is speculation, and that just aren't backed up, and that's pseudoscience to me. Everyone has speculation, and I think a lot of mathematicians and physicists, some of them hide it very much. But there are others that I respect immensely who speculate, who say, to me, a great physicist will give you a question and say, nobody knows the answer to this question. That to me is a hallmark of a great physicist, because they're working on the great open questions. Let me know what you think. Hope you're having a good day. And that's it for today. Thanks. Bye.